Honors Algebra 2 Pre-Calculus. We're doing 10.8 in Pre-Calc, which is polar graphing. So the zeros of a polar graph refer to the theta values for which r equals 0. So they can be very helpful if you do have to graph by hand, because these are when the curve is at the pole, right? So a lot of polar curves kind of loop out, do a thing, and then loop back to the pole, and loop out, do a thing, and loop back to the pole. And we've seen that in all the polar graphs that we've done so far. So let's go ahead and find some zeros for each of these polar equations, right? So in A, we're given r equals 1 minus 2 sine theta. So what I'm going to do is I'm going to set 0 equal to 1 minus 2 sine of theta, right? So I don't care, I'll move the 2 sine theta over, it doesn't really matter which one I move. When I divide by 2, I get that I want when sine of theta is 1/2, which is when the y on the unit circle is 1/2. Well, that happens here and here at pi over 6 and 5 pi over 6, but also at every one of those values forever and all eternity, right? So my two zeros would be at pi over 6 plus 2n pi, meaning as many full circles as I want, and 5 pi over 6 plus 2n pi. Meaning that I could have, so pi over 6 would be a spot where I'd have a 0, but so would pi over 6 plus a full circle, so plus 2 pi, which would be 13 pi over 6. So would pi over 6 plus 100 full circles, which would be pi over 6 plus 200 pi. All of those would be equal places where I have zeros, right? So that's the idea behind that 2n pi. If you're given a window where if they say find the zeros from 0 to 2 pi, well, then I would only need these two zeros. But if I'm not given a window, then I have to understand that there are actually infinite of these same zeros. Second one is when r equals 3 cosine 2 theta. So I'm going to set 0 equal to 3 cosine of 2 theta. Right, so 0 equals cosine of 2 theta. Well, cosine is the x on the unit circle, right? So I want where the x on the unit circle is going to be essentially is be a 0. So that's going to be at my pi over 2's, right, here and here. But again, the trick here is that I'm going to have to divide by 2 at the end of the day, right? So what's going to happen is I'm going to get that 2 theta equals pi over 2 plus 2n pi, meaning a full circle, right? And 2 theta equals 3 pi plus 2n pi. Now, there is a little caveat here that I'll walk you through in a sec. If I solve both of these for theta, I end up getting that theta is pi over 4 plus n pi, or 3 pi over 4 plus n pi, and those are fine. I could give those answers in conjunction together. But there's another way to do this, because in this rare circumstance where the two answers are 180 degrees or pi radians apart, I could actually write both answers as pi over 2 plus n pi. Because instead of saying pi over 2 is an answer by itself, I could recognize that if I add pi to pi over 2, I get 3 pi over 2, and so on forever. If I had done that, right, since that's 2 theta equals, the other way I could write this answer is that theta is pi over 4 plus n pi over 2. So this would also be an alternate way to write that answer. So those are the times. So essentially, what's going to happen is at any of these times, the circle is going to loop back, like the shape is going to loop back and touch the pole. So in our example 4, we're actually going to graph this curve, because you might be thinking, hey, that's an awful lot of times that it loops back to the pole, and I'm going to show you what this graph looks like and why it's kind of cool, and then we're going to segue into a lot of polar graphs that we are going to do on a calculator because they're very daunting and annoying to do by hand, but polar graphs look super cool, and if you have one of those fancy calculators that has different colors for different graphs, you can make some really cool like flower shapes and fun stuff if you're just like bored and you want to do some cool graphing. So what we're going to do is in example 4, we're going to actually graph this r equals 3 cosine 2 theta.